set the tone for engaging and insightful event. As we continue to the journey today, I would like to extend my sincere gratitude to the Institute of Engineers India for graciously hosting this virtual webinar series, which is a two-day event in association with McAfee and with the invaluable support of World Federation of Engineering Organization. Your collaboration and commitment towards the advancing engineering knowledge and sustainable infrastructure solutions are deeply appreciated. Today, the second day of the Reinforced 2025 promises another round of stimulating discussions, technical presentations, and shared learning as we continue to explore innovative approaches in geotechnical and civil engineering. I encourage everyone to stay actively involved and make the most of the collective expertise we have brought together here. Uh, Thank you once again for your presence and your support. Let us start with the day two of the session. So to start with this technical session, the first technical session, I would like to invite Dr. Madhvi Lata on innovative geosynthetic solutions for enhanced soil reinforcement. Dr. Lata is a professor in the Department of Civil Engineering and chair the Center of Sustainable Technologies at IIC Bangalore. Dr. Madhvi is a fellow of the Indian National Academy of Engineering, and her research interest centers around the fundamental aspect of soil reinforcement and understanding of the shear mechanism at micro level. On this note, I would like to invite Dr. Madhvi Lata.
Thank you, and hope my screen is visible to all of you.
Yes, madam, we can see the screen.
Yeah. Good morning, everyone. And I have this presentation today for you, which is on my recent research. I've been working in the area of geosynthetics for past 30 years since I joined for my PhD at IIT Madras. And we have been working with commercial geosynthetics for all our research purposes so far. And recently we embarked on this journey on 3D printed or innovative geosynthetics. 3D printing is just a tool to explore different possibilities of creating new generation geosynthetics, which is at research stage right now. And with active collaborations, we are hopeful that these solutions can be realized very soon with the collaboration with industry. So let me start with this, one of my favorite slides on the concept of modern soil reinforcement. As Henry Whittle pointed out, when we put these geosynthetic or any in fact, metal inclusions in case of Henry Whittle, inside the soil to support a structure like a retaining wall, we can expect two types of failure, sliding and rupture. And if you want to avoid sliding, the simple solution is if there is some tension, delta T, which is expected in the system, due to active or passive pressure conditions. And as long as the tension is less than this value, which is actually the frictional force, which can be calculated by multiplying the normal stress with the tan psi. Psi is the interfacial friction between soil and reinforcing material. And delta L is the length of interaction between soil and reinforcement. And two, because we have two sides. When you have two layers of granular soil and you have this geosynthetic layer in between, and there is this tensile pull acting on this reinforcement, and then as long as we are within this limit, we will not have any sliding failure. At the same time, as long as the tension applied on the reinforcement is less than the tensile strength, allowable tensile strength of the material, we will not have rupture. So if you look at the Mohr circles for this scenario, let me just put this pointer. Yeah. If you have an unreinforced soil, the normal stress shear stress response is something like this, where you can expect a failure in some cases as when you have low shear strength. And if you are trying to put some confinement into the system, then the Mohr circle shifts to the right, making the failure kind of a case which is most likely not possible. And if you put reinforcement, then the reinforcement further improves the sigma 3 or the confinement effect, and Mohr circles further shifts to the right, and hence we will not have any possibility of failure. This is the condition. And then With this context, we use reinforcement for different geotechnical structures, including retaining walls, foundation beds to enhance the bearing capacity, and slopes to support against sliding and then other kinds of failures. And when you construct an embankment over weak foundation soil, we use reinforcements either inside the embankment and also below the embankment to support these loads, and also in paved and unpaved road systems to support these cyclic loads and also to enhance the uniform load distribution. Now, coming to the innovative geosynthetics I'm talking about. Today, I will discuss 5 different innovations that we have tried to come up with. One is we have geogrids with different aperture shapes and sizes. And then we also have geogrids with texture on their surface. And then we have a new class of geosynthetic system called geocell anchor cage. And then natural reinforcing geosynthetics, which are, of course, in market for a long time, but we have some innovations in this direction as well. And then geocells with waste infill. The first one is 3D printing of geosynthetics, which helped us in creating geogrids of different aperture shapes and sizes to customize to our needs of research currently. We have this fused deposition modeling type of printer, FDM printing, what we call in 3D printing. There are different types of 3D printing methods available in market, but for polymers, the best suited method is FDM, fused deposition modeling, where we can print the material in layers. We have this 3D printer in our lab, which can build a volume up to half a meter height, half a meter width, and half meter length. So half a meter cube of material can be printed in this system at a time. It works on a simple mechanism that you have a filament spool in which you can feed filaments. Right now, polylactic acid or PLA and polypropylene or PP can be used as a filament in this system. The filament comes to an extruder head, and where it is connected to a nozzle inside which the temperature is increased to a level that the filament melts. And then there is a touch bed on which you can print the material. To give the instruction and control the printing, we have this controlling panel where we can set the temperature according to the material or filament that we're using, and then we can control the speed of printing, and we give the input of the entire printing model. We can create a G code, what we call. This G code is generated through various simple software tools, including in AutoCAD. We build this volume layer by layer, and then we use another supporting software to create this code, which tells the system what is the length, width, and height, and apart from that, how many layers, which direction you need to print. And you can customize this entire printing as per your need. It is not like we have one material and then we will have one system. Each part of this component that we are printing can be customized. Now, just let me just this is the printing of geogrids that I'm mentioning about. Here you can see the entire printer, and we have used polylactic acid filament, which is coming into the extruder head. And here you have this nozzle in which the material melts. And then we have already given a G code to the system, which tells you like the dimensions and geometry of the geogrid and the direction in which you can print. This is a simple square geogrid which is being printed here. Now, we try to print different shapes of geogrids. One is square. The square geogrids are biaxial geogrids are very common in our practice. And we also have triangular geogrids in recent times and hexagonal geogrids. There is also an interax geogrid, which has this kind of a web kind of a structure. So there are different types of these geosynthetics are recently available in market in smaller quantities, but not much research has gone into the way in which these different aperture shaped geosynthetics interact with soils. So when we try to print these with the same aperture area but different aperture shapes, what we realized is when we compare the tensile strength of these materials, obviously the square one has the tensile strength like this, but the maximum tensile strength is reported by the Interax geogrid. There's also a table which tells you that the square geogrid has the least tensile strength and Interax geogrid has the highest tensile strength. These values are little low here, mainly because we used PLA, which is low strength polymer. And when we also conducted interface shear tests on these different aperture shaped geosynthetics, where the lower box of the direct shear box and the upper box are filled with sand, and then you have a geogrid at the interface, and we apply shear, and we also do the PIV analysis to understand the shear zones that are developed. We realized that the angle of internal friction is the lowest in square geogrids, and Interax obviously has the highest angle of interfacial friction. In between, you have triangular and hexagonal geogrids. This is not just enough for a fair comparison. We need to compare these geosynthetics against a real case. So we have taken this retaining wall case. I just want to explain like how much material we might have to use to get the same factor of safety against sliding and overturning and all other failures. So you have this retaining wall, a simple cantilever retaining wall with many reinforcing layers. So there are some hypothetical height and unit weights assumed. And then the angle of internal friction of soil is also 30 degrees in the backfill, and the same thing is used in the reinforced system as well. And then there is some dead load and there is a live load, and we need factor of safety of 1.5 against rupture and pull out. This is the criteria. Now, when I try to put these different geosynthetics or geogrids with different aperture shapes and calculate these factors of safety, and to arrive at the minimum factors of safety against rupture and pull out, we made the calculations, and this is the length and number of reinforcement layers required for different shaped geogrids, and then the surface area of the material used, which tells us the economy of the entire reinforcement system that we're going to use. So when you make a comparison on the percentage reduction in the material consumption compared to square geogrids, the square, there won't be any material reduction because it is square to square comparison. And in case of triangular geogrids, you have 16.5% saving in material, and hexagonal geogrid gives you 60% more 60% reduction in the material consumption compared to Interax, which gives you 50, which means that though Interax is very good at tensile strength and interfacial friction, the hexagonal geogrid is actually giving you large savings in the material because the arrangement of its ribs in 6 different directions, which resists pull in all these directions with least material. Now, moving on, we also want to try geogrids with various aperture sizes. From times immemorial, we have been using geogrids with similar aperture sizes in our research. Of course, this aperture is very big, which saves us a lot of material, a lot of sand particles or aggregate particles go sit in these apertures. That is the main function, which is reinforcement. But we are trying to explore other functions of geogrids, which can be enhanced with different aperture sizes. Here we are trying these 4 different aperture sizes. When these geogrids are interacting with sand, with particle size ranging about average particle size is about 3 mm, then we try to have these geogrids with the aperture sizes starting from 2 mm, then we have 3 mm, 4 mm, and 5 mm. In case of 3 mm, our aperture size is exactly matching the mean particle size of the sand, where here it is less than the mean particle size, and in other 2 cases, the aperture size is bigger. Then when we try to do the angle of repose test to calculate the rough residual friction angle, then obviously we see that when the aperture size matches the average particle size, we have the maximum the residual friction angle, which is about 41 degrees. In other cases, it is slightly lower. Now, the interface friction or the residual friction angle is not the only criteria. So we have to test these systems in various applications. For example, I took the application of liquefaction of soils, which can be quantified using cyclic simple shear setup that we have in our lab. Cyclic simple shear setup is much superior to cyclic triaxial system when we are trying to estimate the liquefaction potential of soils, because here we are applying pure friction, pure shear on the soils, which is the right simulation of the exact field conditions when a shear wave passes through the soil. Whereas in case of triaxial test, we are imposing compression and we are trying to shear the specimens. So when we have the cyclic shear system, and then you have a sample in which you put a layer of geogrid at the center with different aperture shapes, one matching exactly with the average particle size of the sand, others either less than the average particle size or higher than the average particle size. And there's a very interesting result when we compare the stiffness degradation of these materials. The sand-alone test has a kind of stiffness degradation shown here. The other specimens with the aperture sizes actually not matching the average particle size of the sand, either less or more. All of them have shown a quick degradation of the stiffness, whereas the system which has the exact aperture size as the average particle size showed very slow stiffness degradation. This is very obvious because these three are obvious results, because when you have reinforcement in the system, sand to sand friction is reduced, and we are replacing sand with partially with polymers. Polymer sand interfacial friction is definitely lesser than the sand to sand friction. That is the reason we have stiffness degradation. However, when you have the polymer with aperture size, the grid with aperture size matching the average particle size, you have very slow stiffness degradation. And then when we compare the excess pore pressure ratio generated in case of cyclic simple shear test, when we are trying to see the liquefaction potential, sand alone sample, that is, there is no reinforcement, it is actually liquefying at about 100 cycles because of the high density of the specimen. All these geosynthetic reinforced specimens whose average particle size and aperture shape do not match are failing much before the original sand. Whereas the specimen with average particle size matching the aperture size, then you have the maximum resistance against liquefaction. The same can also be seen with the hysteresis loops, what we are plotting, shear stress versus shear strain. The hysteretic behavior clearly shows that the loops widen very quickly in all other cases, except in the case where your aperture size is matching the average particle size. Now we coin this word called aperture ratio, which tells you the mean particle size, aperture size divided by the mean particle size of the specimen. So as long as the aperture ratio is exactly 1, you have the maximum resistance against liquefaction. How do you use this? When you use this kind of system like aperture ratio matching the particle size, it becomes very uneconomical for creating a reinforced system because your material consumption is too high. And also we don't need this kind of a system for other functions. So just to enhance the liquefaction resistance of the sand, we can have one layer of a very low strength geogrid below the actual geogrid which is used for reinforcement, so that you have a aperture ratio is 1, and then this performs only the function of liquefaction resistance, whereas the other geogrid with larger apertures can provide the function of reinforcement. Now, the principle behind this behavior is very simple. When you have aperture size smaller than the particle size, only a little bit of portion of the sand gets interlocked with the aperture, and then very easily this particle can be displaced in shear because of this interlocking, low interlocking. Whereas when aperture ratio is 1, your interlocking is perfect. The material, the particle goes and sits inside the aperture, and you need very high shear stress to displace this kind of a particle. Whereas if you have higher aperture ratio, then you have this particle has a gap between the walls of the reinforcement. So within the reinforcing geogrid, this particle will roll and get displaced, and that is why your shear stresses to displace this particle is also lower compared to the case where your aperture ratio is 1. So when we look at the shear bands produced in the particle image velocimetry in shear tests, you can see that we also have a comparison of shear band thickness. You have the maximum shear band thickness in case of particle size and aperture size matching, whereas all other cases your shear band thickness is less. This tells you like intense interactions happening at the interface when you have aperture ratio of 1. So this is a new class of geogrids which have secondary function in the reinforced systems that can enhance the liquefaction resistance in case of dynamic earthquake loads. Now, the next class we are looking at is textured geogrids. If you look at the commercial geogrids, most of them have very smooth texture. As far as I have seen, most of them are with very smooth texture. So, texture is an important parameter in geotechnical systems because it enhances the interaction between two different materials. So, we try to create different geogrids with different aperture shapes as well as different textures. Here I am looking at this diamond type of texture. One-way and two-way textures are considered in all three different shapes of geogrids, and we compared with the smooth as well as textured geogrids. All these are created with the FDM 3D printing as well. And then you have square, triangular, and hexagonal geogrids with and without texture. And then when we did plate load tests with reinforcement in form of untextured and textured geogrids of different shapes, then we see that without texture, your bearing capacity ratio is varying from something like 1.1 to 1.3 kind of a thing. And if you have one-way texture, you can further increase it to up to 1.7. When you have a two-way diamond texture, we could see that the bearing capacity ratio is increasing significantly, going almost to 1.75, which is a very, very good sign. The bearing capacity ratios are not too high here because of the low strength geogrids that we're using. But this can be implemented in high strength geogrids as well with other manufacturing techniques. And this clearly shows that by putting texture on the surface of the geogrids, you have excellent improvement in the bearing capacity ratio. So the mechanism here is when you have smooth geogrids, the kind of mechanism you can expect is particles get entrapped and interlocked within the geogrid aperture. And then the ribs of these geogrids also provide passive resistance to the motion of the particles. Whereas when you have additional texture on the geogrid surface, apart from the passive resistance offered by the ribs, you also have resistance due to surface texture. Additionally, this is one sample of the exhumed geogrid after the test. Within the texture, the particles go on sit and then they enhance the sand to sand interaction instead of sand polymer interaction, which is mainly responsible for the increased load carrying capacity and shear resistance. Now, towards geocells, as all of you know, geocells were invented as a kind of reinforcing system for immediate needs, immediate load support in 1970s. And originally, they are made for providing support on the structures which are moving or resting on soils of very low shear strength. Now, geocells have evolved over the time from 1970s, and now we have this kind of versatile geocells, which can be collapsed and brought to the field and expanded and filled with the soil. And they can be used for different applications like below the foundations for increasing the bearing capacity, below the embankments to provide the load support on soft clays, and then below the road, in the roads in different layers to enhance the shear uniform stress distribution and cyclic load resistance. And they can be also used as facing for the retaining walls. Excellent stacked facing with geocells. They are also used for erosion control. Now, this is the evolution of geo cells I am showing here. And since 1970s, there is a change in shape. Originally, they were in square or diamond shape, and then they moved to rectangular chevron patterns to the current honeycomb pattern, which gives you the maximum enclosure with least perimeter. And then the surface was originally very smooth, and they are now made textured, and they also have perforations to allow drainage. Originally the material was paper or aluminum, and now currently we have high density polyethylene and polypropylene geocells. Connections were originally made with staples or like Bodkin joints. Now we have moved to ultrasonic welding process. All these are great advancements, but still there is one small advancement that can definitely enhance the reinforcing potential of these geocells, which I have thought about, and we have tested and established this. This is called geocell anchor cage. To go to the geocell anchor cage, first I will tell you why geocells are an excellent form of reinforcement compared to planar geosynthetics like grids and geotextiles. When you have geocell, it has multiple functions. One, it provides all-round confinement to the soil, and then it also provides a beam effect, which acts like a mat foundation to the load, and it also has a membrane effect when it is bending under the load, and it also provides an anchorage effect because it has sufficient thickness along which you can enhance the interaction between soil and geocell outside and inside. So originally Bathurst and Karpurapu have shown that how this additional confinement can be quantified from simple Mohr circles, and I have extended this theory to multiple geocells through my PhD at IIT Madras. And this is through Mohr circles how we can see that delta sigma 3, which is the additional confinement due to geocell, can be converted and quantified into the apparent cohesion, which is induced into the soil, which is otherwise cohesionless. Now, this is proved through multiple experiments and element tests and field tests. This is a cyclic triaxial setup that we have in our lab. 300 millimeters by 600 millimeters specimen can be tested. This is an aggregate sample which is tested, and you can see that when you use geogrids, you have necking of the samples at locations where geogrid is placed, whereas when you have a geocell, it is perfectly standing without any disturbance throughout the length of the 600 mm is like more than half a meter size. So this is a perfect example how geocells are very useful, not just because of the material that we use, but mainly because of the configuration of interconnected cellular network. Now, this is also tested in field. Professor Babu and myself were involved in this project where we have used these different forms of reinforcement to reinforce village roads in the district of Shamrajnagar in Karnataka. And we realized that geocell reinforcement is most effective in terms of reducing maintenance cost and improving the durability and long-term rideability of these roads. Now, the enhancement that I am discussing today is in the form of a geocell anchor cage. Geocell anchor cage is the geogrid, basal geogrid, which we generally use in geocells. We have a basal geogrid. And then to the geogrid, we can actually we provide anchor pins such that each anchor pin goes and sits exactly at the center of each geocell pocket, so that the stress distribution within geocell can be extremely uniform. Otherwise, since the geocell pocket size is large, we have non-uniform stress distribution within geocell pockets. This can be translated to the Mohr circle as well. You have additional confinement and additional apparent cohesion induced in the soil due to geocell anchor cage. This is a project I executed for SERB, and we have got excellent results and publications through it. So this is the concept of geocell anchor cage, where you have a geogrid with anchor pins which will be placed exactly at the center of the geocell layer. But this can be on top or bottom. So which configuration is better is what we researched also. And to manufacture these geocells with the central geocell anchor cage, again we used 3D printing. Here we used polypropylene to create geocells. These geocells are printed in the lab using FDM 3D printing. You are seeing the sheet of polypropylene being printed, We tested different configurations of printing, horizontal, vertical, and diagonal. And then we realized that this is the polypropylene sheet that we are printing. And then these are different orientations, and we realized that the diagonal printing gives you the maximum tensile strength as well as interfacial friction, because the horizontally oriented fibers get separated easily where they are fused within the joints, and vertical ones will only provide resistance along the filaments, whereas diagonal ones have both fiber strength and the adhesion between the filaments coming into the rescue when tension is applied. So this is also tested in interfacial friction, and intuitively you can see that the diagonally oriented polypropylene sheets provide maximum interfacial friction because of higher resistance offered to the motion of particles in the direction of shear. So now these polypropylene sheets are ultrasonically welded. We have developed a special horn for making these geocells within our lab. This is the ultrasonic welding system with a specially fabricated horn where we can weld the PP sheets. So far, in the world, this is the maximum closer size that geocells are manufactured. This box type of geocells are 3D printed using the FDM printing that I have shown. But we were able to make exact polymeric shape. I mean, now we have moved from making polypropylene sheet and ultrasonic welding to directly printing the geocells. Very recent research that is yet to be published, but these are like printed from polypropylene sheets. Now the question here is the anchor cage. How do you manufacture? This is the anchor cage 3D model, which is developed in AutoCAD and then converted into an STL file, which is needed for the 3D printing. And this is the 3D printed geocell with 3D printed anchor cage. This anchor cage is made of polylactic acid. Now, you have this load test on these geocells with anchor cages in different configurations, upside down and low up, top down and bottom up kind of configurations. And we see that the one where we keep the bezel geogrid at the bottom with the anchor pins facing upward give you the maximum bearing capacity and reduced settlements. You can see that the anchor cage one with the geocells up to 3 times the breadth of the foundation, both up and down configurations. The bottom one is much superior to the top down configuration. Now, this is equal to when you have 3 geocells with a simple anchor cage, gives you same reinforcement benefit as a 4 geocell reinforced configuration, which gives so much of savings in the materials. Now, quantifying the bearing capacity ratio, you have almost 2.75, 3.5 bearing capacity ratio with geocell with anchor cage compared to without anchor cage system. So the reduction in settlements is also more than 60% when you have this geocell anchor cage because it provides bezel support, and also there is a mechanism which I'm going to explain now. This is the top and bottom configuration. And if you have this geocell layer, you have this all-round confinement effect acting like this. Primary confinement due to geocell. Now we have a bezel geogrid with anchor pins, and under the load it tries to bend and the pins converge. Now you have this additional confinement effect due to the pin, and then you also have the anchor pin acting as a shear connector, and then the soil acting as a frictional medium. So the entire system of geocell plus bezel grid and anchor pin becomes one system with frictional sand in between and additional confinement due to pin, which is responsible for this enhanced bearing capacity ratio, almost 3.5 times the original bearing capacity. Now, if you put the same anchor cage in the top, at the top, and you are missing the bezel support, and the pins diverge instead of converging, so that reduces the confinement effect, and that is the reason for lower reinforcement benefits of this kind of configuration. And when you look at the surface heaves, the top configuration gives you still some heave, whereas the bezel grid with anchor pins gives you absolutely zero surface heave. And the distribution of stresses below the foundation, for case of unreinforced soil, if this is the pressure bulb, if you have geocell which is having thrice the breadth of the foundation as the width, then it actually the pressure bulb. This is the main action of reinforcement, geocell reinforcement. It reduces the height of the pressure bulb and distributes the loads more horizontally. Now, if you have anchor cage, it further reduces the width of the depth of the pressure bulb and enhances this load distribution, which is very, very helpful in case of pavements. And then you have multiple benefits of these geocell anchor cages. One is you have improved confinement, improved lateral resistance, and improved anchorage effect, because you have 4 faces which are getting anchorage effect. And the beam effect also increased because of enhanced stress distribution. And you also have a membrane effect enhanced because of the additional tensile strength offered by the anchor pins. Now, when we are talking about earthquake resistance, how this geocell anchor cage or geocells can be helpful is a very, very interesting topic, because for earthquake resistance, the main function which is needed to be put up by the reinforcement is ductility. Because the more ductile the system, the higher will be the earthquake resistance of the system. So, for example, you have the boat riding on a wave. As long as the boat moves along with the wave, there will not be any damage. Similarly, a reinforced retaining wall, when there is an earthquake, which is very flexible and tries to provide deformations in line with the movement of the shear waves which are passing. And once the shear wave recedes, the retaining wall comes back to its almost original position. This is called flexibility or ductility, which is offered by reinforced systems in general. But now with enhanced reinforced systems, you can improve the ductility furthermore. If you have a simple representation of how horizontal earthquake force acts and horizontal movement of the wall happens, in case of a gravity retaining wall, the movement is very less because it's a rigid system, and that causes a brittle type of failure or collapse. Whereas in case of reinforced retaining walls, the wall allows sufficient movement. That is why it performs in a ductile way, and it is resistant to earthquake forces to a large extent. This is proven through different case studies across the world, how reinforced retaining walls are very, very earthquake resistant compared to other types of rigid walls. Now, we also have this established in through several research thesis published in our institute, starting from Professor Murali, who did his first studies on seismic response of retaining walls through shaking table studies. Till now, a lot of people have worked on this specific topic. This is one very interesting geocell retaining walls made with GeoNet, very simple GeoNets, how they are performed earthquake seismic resistant way when we are subjected them to high earthquake forces in a shaking table. And this shows you why these geocell walls are more flexible and they are earthquake resistant. In case of rigid wall, when we compare, this is the kind of deformations that you expect. At the top of the wall, you have the maximum deformation, and the base of the wall doesn't move because of it is fixed. Whereas in case of geocell facing, you have this distribution equally along the height of the wall, which reduces the movement of the wall. So that is why you have very less deformations under the influence of earthquake forces. Now, we can also use 3D printed geocells. 3D printed, there's PVC geocells, which can be made low strength geocells. But like I already said, the strength of geocells or the reinforcement action of geocells is mainly due to the cellular confinement network and all-round confinement, beam effect, and membrane effect. So even low-strength geocells are very, very useful or beneficial in reducing deformations under seismic loads. And now the geocell anchor cage concept can be still extended to retaining walls, where these are the 3D printed geocells with anchor pin at the center. So you can make a geocell wall and can test under static and seismic loading conditions. This is an ongoing PhD work by my student Arya Krishna, and this will also soon be published. So we see very promising results in this area. With simple intervention in the form of geocell anchor cage, we can actually increase the load capacity of the retaining walls to a large extent, and also completely restrict the horizontal movements of these walls. Now, the next innovation should be in the form of the fill material within the geocells. For example, we use high friction sand. Typically, we use cohesionless soils within the geocell pockets to provide the reinforcement for retaining walls, embankments, and foundations. But the world is running out of sand. All of you know that there is depletion of sand resources, and then we have an immediate need to find alternate materials, and manufactured sand is being used in constructions, and it is yet to enter our geotechnical constructions. If you go in this space, like in the coming days, we will have a lot of problems in constructing our reinforced soil structures if we stick to cohesionless soils with the friction angle requirements as specified by our codes. So we have to look at alternate materials, and the world is looking at alternate materials. A lot of research is being done to convert waste materials like fly ash, construction demolition waste, and other waste from different mine sites into potential fill materials within the reinforced systems. A lot of research is done by VNIT and NTPC also in this direction to create sand and aggregates from the geopolymer fly ash. And at IAC also, and IIT Bhubaneswar also recently I visited their lab, and I realized that they are also trying to create sand particles from the sand particles with adequate friction from the waste materials like fly ash. And at our lab also, we're doing a lot of research on different mine tailings, how we can convert them or potentially use them along with our reinforced soil systems to reduce the consumption of natural resources. So to do this, we have this very fine micro level research going on where we can actually create this sand particle shape and size. When we are trying to manufacture sand, it's as well a very good sand with sufficient particle friction and also sufficient roughness of the surface so that we can get maximum benefits out of interfacial friction and the overall internal friction. So this is the micro CT of sand particle, the natural sand particle, which can be converted into a geometric shape through spherical harmonics. You use micro CT to create this, to get the shape parameters, and then use mathematical formulations to create the geometry of these particles, and do the research on what type of particle shape and size and surface roughness gives you the maximum internal and interfacial friction, and use the waste materials to produce these sand particles. These are the 3D printed sand particles from resins. These are printed from resins using polyjet printing technique. We do have a multi-material printer in my lab where we are printing these sand particles using different types of resins, replicating the natural sand particles as closely as we can with tweaked geometric parameters to get the maximum benefit out of them. And further, we might also research on different materials, including glass, which is being explored worldwide to create sand, which can be used for infill within our reinforced soil systems, and construction demolition waste as well. A lot of research is being done in our sustainable technologies group of IASC, where construction demolition waste is being used to create these cohesionless materials for constructions. Now, the sustainability considerations across the globe force us to use natural materials in our construction. This is a picture taken from NASA in 2022. You can see the heat stress across different parts of the globe, and you can see the concentrated heat stress within our country as well. So the climate action requires immediate remedies for this. To improve the life on land, life underwater, we need to go towards good health, well-being, and responsible consumption, lower carbon footprint materials, where our plant-based biodegradable materials come to rescue because they are very cheap, they are biodegradable, they are sustainable. The only problem there is they are of very low strength and they actually are not sustainable for a long term. So we need to find methods in which making these materials sustainable for long term and also increase their interactions with soil so that we get benefits as we are getting from the polymeric reinforcement. We are working on this. There are materials like coir and jute, which can be potentially used to make geocells, geogrids, geotextiles as well. And they already have enhanced interfacial friction because of their natural surface texture. But the main problem is the tensile strength, which is comparatively low. But these can be enhanced with the interventions like geocell anchor cages that I mentioned before, so that the reinforcement of the system is equal to the reinforcement provided by polymeric geosynthetics. The only concern is the long-term sustainability. I'm also working along with the chemistry group of IISc to provide solutions for the non-biodegradability and hydrophobic nature of geosynthetics when they come in contact with water and soil. So that's still at a research stage. But to give you a brief on how these materials can be extremely beneficial under conditions prone to liquefaction, we try to do cyclic simple shear tests with coir fibers. And interestingly, a lot of earthquake liquefaction resistance is exhibited by the samples which are reinforced by coir fibers. If a natural sand failed within 9 cycles, the liquefaction happened, whereas a sample specimen reinforced with coir fibers to 0.75% by its volume showed resistance up to 65 cycles, which is a great significant improvement. And the stiffness degradation is very, very slow in case of reinforced specimens. And then we also did shaking table model studies to check the large scale applicability of this. And then we see that the unreinforced specimen failed uh, quickly under shaking, whereas coir reinforced model did not fail or did not liquefy even up to large shaking. So the main mechanism here, the pore pressure response, you can see that very, very low pore pressure response. The main reason is when you are applying shear, the coir fibers are getting stretched, and that provides additional tension, which opposes the movement of particles. Also, the interstitial pressures within these coir fibers actually reduce the pore pressure propagation through from bottom to top, which is the main reason for liquefaction resistance. So this research tells you that there are ways in which we can use natural materials into our geotechnical systems for secondary functions like liquefaction mitigation, which has to be explored in the future. And there are sustainability considerations which make all the innovations that I've shown in today's presentation very sustainable, because we can explore eco-friendly options with technical interventions. We reduce a lot of waste through smart manufacturing, and we reduce carbon footprint because we use less material and natural resources are used very less, and we use automatic construction methods. And this is how this becomes a very sustainable um, thinking process towards achieving the sustainable development goals. Thank you so much.
Thank you, Professor Madhvilata. And I must say this was a very energetic session that we had, and marking the very first session to be highly energetic. So we'll be quickly taking few question and answers Q&A session. Okay.
Yeah,
So
sure.
yeah. So let us take first question is from Mr. Haldar. Question says, in earth retaining structure, can I use GeoGrid in layer by layer? It can reduce the thickness of earth retaining structure.
I didn't quite get the question. GeoGrids are being used layer by layer. It is not about reducing the thickness of the retaining structure, because the height of the retaining wall remains the same. The higher the height, we have maximum benefit, right? We are going to increase the height of the retaining wall by putting reinforcement, because we are able to stop the failure due to overturning and sliding even up to larger heights. So the purpose of reinforcement is to increase the height with the same material.
Thank you. So next question is from Mr. Mandal, and question says, how does the installation damage will affect the texture of the geogrid, which will affect the increase in BCR?
Yes, it's a very interesting question. Yes, the geogrid texture, when you are trying to put large boulders, it can actually become flattened. So this needs some research. Definitely, I'm not saying outright that no, nothing happens to the texture. But most of the time, the texture what we are providing is not sharp in nature. It's a kind of flat texture. I have shown a diamond shaped texture which has flat edges. So as intuitively, I can think it will not get damaged by installation or passage of vehicles on it, but it needs to be tested.
Okay, thank you, ma'am. Next question that we have is why these systems are not applied in SH and NHS?
This is, I told you, this is still in the research stage, and we need to establish collaborations with the manufacturing industry and geosynthetic industry and government of India to make these systems realistic. Because right now, what we have published, and we also have two patents on this. One is on textured geogrid and one on this geocell anchor cages. But to make them work in field, we need to show in a large scale. Scenario which we are trying, yeah, hopefully in future.
Okay, so next question that we have is what is the effect of drainage when geocell grids are used in sub-base improvements?
Yeah, geocell provides perfect drainage. It has perforations on it on its surface, so drainage is not an issue at all in case of geocells. That is the reason they have perforations. Even basal geogrid allows free drainage, so absolutely no change in that.
Okay, thank you, ma'am. So the next question that we have is, can you please briefly explain the recent failure of NH construction in Kerala? If you know the possible reason and remedial measure with respect to your research experience.
I cannot exactly comment on this particular failure, but any retaining wall failure have multiple reasons. So something can go wrong. The most possible failure is the construction quality. What is there in the design and drawing may not be exactly built on the ground. That is the main reason most of the times uh, there are failures.
Okay, thank you, ma'am. Question is from again Mr. Mandal. How does the durability of coir mix with sand against its liquefaction mitigation measures?
Yeah, Coir is excellent for liquefaction mitigation. I am not me, many other researchers also have shown that coir, when mixed with sand, has excellent liquefaction mitigation potential. But we need to see how we mix it with sand. That is our risk. And the second thing is long-term durability. Coir on its own, though sand is not really wet. Usually in our systems, it is in dry condition and there is not much microorganism growth for degradation, but still coir being coir, it can be degraded in short term. So we are trying different methods to enhance this time for degradation by putting some latex, natural latex, plant-based latex coating on the coir so that it can stay for, instead of say 7 years, it will stay till 14 years. That was a good um, improvement. That's what we are.
Okay. So I think we can conclude our very first session. Thank you, ma'am, for taking the question. So let us move to our next speaker, Dr. A. Murali Krishna, who will present on geosynthetic reinforced shallow foundation. So I would like to invite Dr. Krishna. So,
Yeah, hi.
so Dr. Krishna is a
Can you
professor
hear
of,
me?
yeah, doctor.
Okay, okay.
I'll just give a brief. Dr. Krishna is a professor of geotechnical engineering at IIT Tirupati. Research interests include earthquake geotechniques, geosynthetics, and ground improvement, deep shallow foundation. He supervised 8 doctorals and 35 master students, co-authored nearly 220 technical publications. On this note, I would like to invite Dr. Krishna. Thank you.
Thank you, Mr. Sumit.
Yeah.
Introduction. Can you see my presentation?
Yes, sir.
Okay. Is my voice is okay, clear?
Yeah, perfect.
Oh, great, great. Okay, so good morning, you all, and thanks to McAfee team for organizing this event, Reinforce 2025, focusing on the future of resilient engineering. So the event being organized by Institute of Engineers, McAfee, and WFEO. So it's a good initiation and bringing out all the people, experts on reinforcement. So I have chosen the topic on studies on geosynthetic reinforced shallow foundation. I thank my previous speaker, Professor Madhvi Lata, and who's my supervisor at ISC for my PhD program. As she mentioned, yes, I was the first student to conduct the reinforced soil retaining wall shaking table experiments, and of course working continuously with different topics. So this is my content. I briefly arranged it like this one. I briefly touch about the sustainability and resilience, and talk about shallow foundations, what is the need for ground modification, and various options. And then I'll take to the geosynthetics for shallow foundations. So as from the previous lecture and yesterday lectures also, I'm sure all of you are aware of different types of geosynthetics, different forms. So how those things, those combinations can be used in the shallow foundations is outlined. And then I'll take some experimental studies and starting from the Benkut and Lee and other recent studies. And particularly, I focus on subgrade strength effect on the performance of geosynthetic reinforced foundation. That's what my primary goal. That's what I'll focus. And then some observations and comparative performance and the concluding remarks. This is what I have planned my presentation. So before going further, I would like to acknowledge the people. Dr. Argadi Biswas, who was my student, PhD student at IIT Guwahati, and who is now working as a faculty at Jadavpur University. And the student has been co-guided by Professor Sujit Kumar Dash, who is now currently working as a professor at IIT Kharagpur. And of course, Professor Sirish, who is working in IIT Hyderabad. So we were contemporary at IISc. So during my PhD time, he was doing several of model studies on geocell reinforced foundation. That's where I was exposed to the geocentric reinforced foundation systems. So as I said, a preamble, so we are witnessing a significant infrastructure growth in the country. Of course, any country to be a developing nation, its infrastructure growth is of primary importance. So, and while infrastructure development, we have to ensure the resilience and sustainability in infrastructure development is a primary, very significant aspect which we need to focus on the things. So the sustainability, when you talk about sustainability, so UN United Nations across the globe, they have set certain sustainability goals, a very famous 17 goals which are listed here. So out of this one, as engineers, and we have to focus on the 3 goals. Goal number 9, where industry and innovation and infrastructure. So where the significant part of infrastructure is involved. And the sustainable cities and the communities, where the, again, development, infrastructure, and so on. And a very important thing is the goal number 12, responsible consumption and production. So in developing the infrastructure and current needs and how we use the resources and how we retain for resources for the future generation, etc., we have to see. That's what the primary goals. So this is one sort of sustainability we have to look into for various infrastructure development projects. And another point is the resilience, what we need to ensure. The resilient could be defined in a elaborated way under adverse conditions, under different conditions, and how the structure would perform without much damage, without sustaining to major damage. So, and continuing to work, function its original intended purpose. So that is what resilience, which we have to ensure the things. So we have to see the paradigm shift, like no. So emphasis should be given to the resilience rather than resistance. That's a general code. So not only just meeting the normal factor of safety and meeting the requirement, but under adverse conditions also, how the structure would perform and show its resiliency. That's very important to see this one. So, as part of this national building and infrastructure development, yes, all the civil engineers play a major role in ensuring the sustainability and resilience in the infrastructure what we are developing and where we are involved in this one. So, which requires some special skills, expertise, and smartness in infrastructure development. This basically understanding various new developments, new material, and what are the sustainable approaches, how to enhance the resilience, etc., etc. These are the key elements for which. This is something preamble I would like to set as a context of this one. Now, I'll just take to you to some bearing capacity related issues, bearing capacity theories as a recap of a mode of bearing capacity failures. I am sure you all aware that bearing capacity, shallow foundation bearing capacity, there are three types of failure could be expected. One is a general shear failure, which will occur in the very dense soil, having the typical failure surface of this nature. And other one is a local shear failure, where you have the medium dense and loose sort of the loose soils also will be having the local shear failure. So where the shear mechanism would be demonstrated as this one. So if I must bearing capacity theories and other things, if you summarize the thing. And the other one is very loose and very soft soils are there. You will have the punching shear failure, where the failure will be like in this form. So generally, a general shear failure is a good one, where the soils are good enough. And whereas in the other category, local and punching shear failure types of soils, so there would be some problems might be there associated with the low bearing capacity and higher settlement, etc., etc. In some situations, we need to replace the topsoil when the difficult situations are there, where the bearing capacity things are not meeting the requirements. So this could be a complete replacement, some material involvement and all. So what we are trying to see here today, our lecture is to how we can modify this particular ground, how we can observe its performance and so on. So structures on low bearing capacity deposits, the main problems are associated with the unsatisfactory bearing capacity of the soil. So it's not only necessary that the soil is loose or soft and very loose, and even though in the good bearing capacity in the normal concerns, but under special loading requirements, it is not satisfying. Even the good soil, a good bearing soil, if it is not satisfying the requirement, then also we have to identify some alternative to enhance the performance. And in some cases, at the loads, if the settlements are excessive, and that time also we need to see how to improve the situation, how to modify the ground, and to meet the requirements and to serviceability, functionality requirements also. So generally, what we tend to do is we go for the deep foundations. When we go for the deep foundations, there are different challenges would be there in terms of the equipment, construction, and other challenges, and cost of the structure and so on. In some cases, we can explore the possible ground engineering, ground improvement options. Various methods can be thought of. A simple one is the excavation and replacement with a suitable soil, which can be looked into, or stabilizing with injected additives, some grouting, etc., etc. In very soft soils, where the soft clay deposits and all, one can go for the soft consolidation, pre-consolidation approaches. And some cases, the sandy soils, loose sandy soils, soil identification techniques could also be used. So in a similar trend, as a part of improvement, soil reinforcement is another approach we can look into for modifying the ground and enhancing the performance of the foundation system. What can we do? So how the reinforced soil beds or foundation on reinforced soil bed could be seen this one. So what we do here, we'll be removing the existing weak soil up to some shallow depth below the foundation. and we'll be replacing with the granular soil, preferably granular soil, reinforced with the horizontal layers of high strength reinforcement, geosynthetic reinforcement, metallic reinforcement, etc., etc. Different strength reinforcement can be included, of course. There is applications can be seen here. Applications a frame footing resting on reinforced earth slab. You can see here some part of the soil has been replaced with the reinforced soil. So with the reinforcement layers we can see, and the soil there also you can just see here. And you have the closely spaced footing, combined footing resting on the weak soil. Again, we can replace the thing. Isolated footings where you have different forms of the thing. And storage water tanks reinforced with earth slabs, and even the RUL approaches and abutments, etc., etc. So these are the typical applications. This is the form of the things what we can just see the things. So what are the advantages of these reinforced soil beds? It will increase the bearing capacity, and obviously it will reduce the settlement, of course. And also another big advantage, it will reduce the differential settlement. That's major advantage. It's a whole system will be working as a monolithically, and reduces the differential settlement. And it in many cases it can avoid the deep foundation situations. We can reduce the necessity for deep foundations. We can also go with those one, and sometimes we can change the type of the foundation for a let us say if you want to go for the mat foundation, we can avoid, and some other deep foundations also could be avoided. So there are some advantages what we can just see that. So that's how the reinforced soil foundations. Just going to the studies on reinforced soil foundations. So the whole credit goes to Vinkaton Lee in 1975, where the pioneering work was done. So they have done some model studies concerning the strip foundation. And in that earlier study, they used the galvanized steel strips as the reinforcement, small strips. And they have considered some thickness, which also takes care of the corrosion rate also. So accordingly, they have taken. And the typical foundation configuration they have considered, and different reinforcement layers, different depth below the foundation, and some soft soil below the foundation, etc. Different combinations they have considered. They have tested the thing. And this is the first study, first of its kind there. In arranging this reinforcement configuration, this is a more detailed schematic view. If you see a footing of width B has been placed, and the first reinforcement would be placed at a distance U from the bottom of the footing. And there are, you can see here, for example, there are n number of layers or reinforcement layers are placed. Each of the reinforcement layer is with a width of B. And these reinforcement layers are spaced at a small h apart. This is the typical configuration what people see. And the response of the foundation system, if you look into the thing. So obviously we'll be having some reference reference case. So with unreinforced foundation soil is unreinforced sand is one reference case. And geogrid reinforced or geocellular, some reinforced case, there would be another response. Obviously, as advantage we mentioned that it will reduce the settlement and increase the bearing capacity. Conceptually, theoretically, one can project this one. These are the typical response for the unreinforced sand. This is the response for the reinforced sand. So which is expected to give the thing. So coming to the Vinkaton Lee study, so the results have been obtained. Typical results, findings from several investigations can be seen here. Settlement versus average bearing pressure for a different number of reinforcement layers. You can see here number of reinforcement 1, 2, 3, 4, 6, 8 different layers. And U is a depth of the reinforcement, first layer of reinforcement from the bottom of the footing. At what depth we are placing the reinforcement. So these two are the important parameters what they considered, and they have obtained these results. In general, the observation is the ultimate bearing capacity was increased by 3 to 4 times in various types of tests, and the settlement tilt was brought down by 30%. These are the two things what they have achieved. And also the bearing capacity improvement, bearing capacity ratios have been presented in a non-dimensional way. So BCR is the Q by Q naught, where the Q naught is unreinforced soil bearing capacity and Q is the improved bearing capacity. So for different number of reinforcement for different configurations, how much it has been increased has been depicted in this particular figure. So we can see that number of layers and depth of its first layer of reinforcement and settlement, etc., are the governing factors in improving the things. So Benquet also formulated the how the bearing capacity failure surfaces would be generated within the reinforced soil foundation system. He basically represented as two zones, zone 1 and zone 2, where the zone 1 is moving downwards through the thing. And zone 2 is the zone adjacent to this zone 1, which is being moved upwards into this one. Okay, and the reinforcement, which are the reinforcement here, along the reinforcement, what is the type of the force it is being generated? That also he postulated. This is the a right angle bend, double right angle bend is expected at the junctions, so which will produce the type force to opposite to the towards upward direction, which is opposite to the direction of the loading thing. So the typical way of representing the reinforcement force, etc. So on. This is a starting thing, and several studies were done in modifying different conditions and different things and so on. So there is a way of quantifying this zone, how at a different depth, at what distance this particular failure zone could be developed. This is one study by Shin et al. So where they have quantified the distance with depth, at what depth, at how much, what distance that particular failure zone will be there. This is the minimum distance. This will give us some idea about how much reinforcement length to be provided, so which could be depicted in this particular figure. Some other studies are also there where they hypothesis they presented of how different bearing capacity behavior, means functionality in terms of the generation of the failure surface and the resistance could be there. These are different possible ways of the things which could see the things. And bearing capacity improvement is widely being used for the embankments, storage tanks, which are a large structures, by applying the geosynthetics and reinforcement and so on. So that's a sort of setting the context of geosynthetic reinforced foundations and the preliminary studies and the typical observations what we can see. Now, as I mentioned, different forms of the geosynthetics are there, like uniaxial geogrid and biaxial geogrids and geotextile geomembranes, and these are the three-dimensional geogrids in terms of the geocells. Okay, they are ready-made geocells, etc. So referring to the previous configuration, what was discussed, a typical shallow foundation beds reinforcement configuration could be of this nature. If we are using the geosynthetic, two-dimensional geosynthetic material as a reinforcement, so we can have the multiple layers below the foundation, or we can also use the geocell layer into the foundation system. Several of earlier studies have considered the homogeneous soil, either very soft soil and it could be a sand or clay type material, very soft soil, how the improvement is obtained has been focused. So the typical responses observed from different studies, what we can see the things. So this is one model test setup which was used by Sirish in 2006 for the studying the improvement in the performance of the geocell foundations. A typical configuration of the load setup. So where the loading has been applied and observing the surface deformations and some pressure observations inside also that could be seen. This sort of a plane strain condition simulation to observe the improvement in the performance of the thing. So in general, if you summarize geocell reinforcing foundation system, geocell sand matrices, so which would be having a thickness of H of the thickness of the geocell, diameter of the foundation is represented in terms of the D, and U is the depth from the foundation base, at what depth we are placing the geogrid geocell, so other things. So when you look into the geocells, the aperture opening size is another important parameter. Orientation of the ribs and what is the pattern that is being adopted is seen. And various researchers have focused on different parametric ways, and they conducted different tests our study as done by Argadeep is we focused on the subgrade strength, influence of subgrade strength, and test geometry on the performance of the geosynthetic reinforced foundation. You see here some homogeneous soil to some significant depth is taken. It could be of different strength values, different material. So as a first step, different alternatives are considered. So first step is removing the topsome soil and filling with the unreinforced sand. Generally, this is the common approach. When the soft soil is there, some topsoil will be removing, will replace with the good field material and conducting the test. This is the primary one. And if you are providing one layer of reinforcement, geogrid reinforcement at the interface, this adding one layer of reinforcement at the interface, and as below the in between the good granular soil and in situ soil, one geogrid reinforcement has been shown. And another option, instead of the geogrid planar reinforcement, one can also place the geocell directly onto this original soil and fill the cells with the granular material, and then constructing the foundation. And another option is to have the geogrid at the interface between the original soil, in situ soil, and the fill soil, and over the geogrid placing the geocell as a combination, geogrid and geocell combination. So under these different configurations, and by varying the in situ soil strength, it is not necessarily that in all the situations it's very loose soil. So even though in the other marginal soil, even very good soil, if you are using the reinforcement, how the capacity could be improved, what is the improved performance can be obtained, that's what the study has been conducted and investigated. So in this way, what variables were considered is clay, in situ clay condition. So it could be a very soft clay with undrained cohesion of 7 kilopascals to reasonably stiff clay of having a 60 kilopascals of undrained strength. And the study also considered the different variation of the sand layer thickness, considering the capital H here, which includes the thickness of the geocell and reinforcement, and also U is the top one. So we are considered as these different four variable things. And some other constant values what are considered is the depth of placement. U is constant in all the case, 0.1D. And the pocket cell of the geocell matrix has been considered as 0.8. And the relative density of the infill sand in the surface layer, the top layer sand layer and infill sand has been considered as 80% relative density. And of course, the width of the geocell matrix and base width of the geogrid, it's considered as a B as 6 times the diameter of the footing. This is what the general configuration has been considered. So with that condition parameters, there are 5 series of experiments were conducted to understand the effect of subgrade strength on different parameters of H by D and other parameters, and this is what the experimental program. So we will see one by one. This is the model setup. So which is primarily a 1 meter by 1 meter by 1 meter test tank, and footing of 150 mm diameter footing is considered, and the clay soil having these properties, which is Cl, and the sand soil has been considered having these properties, poorly graded sand, and the geogrid of 20 kilonewton per meter as a ultimate tensile strength with 20 mm square apertures has been considered in doing this. There are some properties of the clay and other materials has been shown here. And for preparing the clay bed, there were several trials were done for varying water content and compaction, and some standardized density and water content values were obtained to arrive the desired shear strength soil. And the soil has been filled layer by layer to obtain the complete test tank filled with it. So, and over that sand has been placed, and sand preparation of the sand bed was done using the sand draining technique. So from the hopper, sand will be poured, which will be dispersed here. So to get the targeted relative density by this method, so there were several trials were conducted, and the height corresponding to 80% relative density, how much is the height required, that much height of the fall has been followed. And this is a typical picture of sand draining technique, a simple one. Of course, there are several sophisticated setups also would be there, where the complete large chambers also could be placed and automatically placed. So geo cells have been prepared using the GeoGrid, and the GeoGrids were cut into transverse and longitudinal members, and they put together longitudinal member, transverse members, and they connected using the Bardkin joints. The strip is considered the Bardkins, so which will be used to form the geocells of this nature. This is the geocell. So various configurations. This is the unreinforced sand or clay bed. This is a GeoGrid reinforced sand. Only GeoGrid has been placed here, and this configuration shows the only geocell here. So this last configuration is the GeoGrid, the base, and geocell come together placed onto the things. So as we have seen earlier, the typical response of unreinforced soil and reinforced soil QR, if you have the thing, these are the two types of responses what can be obtained. And the analysis of these results will be done in terms of the bearing capacity ratio. The bearing capacity ratio, what we do for a given settlement, at any given settlement, let us say SYD is taking some settlement value. At the settlement value, what is the unreinforced bearing capacity or capacity? And what is the reinforced bearing capacity? The ratio of that one, QR by Q naught, will give you the bearing capacity ratio. And another parameter which can also be considered for evaluation is for a given loading condition. Let us say this is a Q is a loading condition. For a given loading condition, what is the settlement in the unreinforced case, S naught, and what is the settlement in the reinforced case, SR? So these ratio also we can just see as how much settlement reduction obtained and so on. And sometimes we can also represent the bearing capacity improvement rate with reference to its unreinforced capacity. Okay, how much is the rate of the improvement can also be represented. So where the QR minus Q naught, the difference between these two, and the ratio with the original one also being represented. This is a bearing capacity improvement rate also can be used for obtaining the some results analysis. So now going to the test results what were obtained. So initially, before going to further with studying with the reinforced configuration things, it is very essential to look into the is unreinforced sand responses. Here, homogeneous clay or sand has been used for testing. So as mentioned, there are four types of the clay subgrades, and one sand subgrade, sand soil also used. These are 7 kilopascals, 15 kilopascals, 30 kilopascals, and 60 kilopascals CU value, how the foundation responds. It's very obvious when you increase the subgrade strength in situ soil strength, we will be getting the improved performance, which has been significantly improved. And another test with the 80% relative density of the sand has been used as a material, and it has been also tested its capacity as a whole. So we can see here the 80% relative density sand is showing slightly lesser bearing pressure compared to the 60 kilopascal then. And of course, this is giving the larger strength compared to other up to 30 kilopascal. And it's also observed the heaving of the surface when you load the thing. Heaving at the surface also has been obtained on this one. Second configuration is having the top some thickness of the soil has been replaced with the sand soil. Again, it's a layered configuration, but unreinforced. There is no reinforcement in this case. When you see the responses, so you can see here dashed line shows the homogeneous soil case, And this solid line shows the layered soil with the sand having the 0.63 times D as the thickness of the thing. So in all the curves, we can see there is a significant improvement in the capacity when we are replacing the topsoil with the unenforced sand. So there's a significantly while conducting the test for different high thickness of the heights, the optimum layer thickness has been obtained as 1.67 D. If you replace the top 1.67 D with the sand, it's the optimum thickness. Thickness we can modify. So these are the some configuration for a given thing. Homogeneous clay is only 7 kilopascals soil having the unreinforced homogeneous soil, and for different thickness of the sand layer, how the improvement is represented here. Similarly, this is for the 15 kilopascals undrained shear strength soil, and for different responses, how the clay plus sand is obtained. So from this one, it has been observed that 1.67 is ideal. Next one is the including the reinforcement at the interface between the sand and clay. A geosynthetic reinforcement has been placed here, and the responses were observed. This is a typical picture what we can see here. So here, this is the geogrid for different undrained shear strength values, and different 0.63 is the thickness were considered. Reinforced sand layered configuration and the reinforced layer configuration again is been shown. So again, you see the from unreinforced case to reinforced case, where is a significant, very dominating improvement with the inclusion of single planar geogrid at the interface has been obtained, irrespective of all the configurations what we can see. We can read and understand what are the different levels and so on. So source upgrades, the thickness, optimum thickness has been obtained as 1.67 times. If we are having the stiffs upgrade, for example, 60 kilopascals upgrade, so 1.15 times the diameter is the thickness one what we can obtain. Again, those results were obtained based on these results for 7 kilopascals, 15 kilopascals, and 30 and 60 kilopascals, having the homogeneous clay and clay sand bed geogrid, how the different performance could be obtained. We can, these pictures are self-explanatory. So next configuration is the geocell reinforced sand, having the over the subgrade soil. So here, the difference with the geogrid, how much is the improvement, and with the geocell, how much is the improvement, the comparison has been presented. In this case, it's not that unreinforced material, but with geogrid and geocell, how much is a difference has been depicted in this particular case. So in the case of, you can see here, very soft soils up to some deformation level, there is not much difference between the geogrid and geocell. So whereas if you see the 60 kilopascal very stiff soil, placing the geocell instead of a geogrid has shown the significant improvement in the capacity improvement. Again, some optimum geocell heights and reduction in surface heaving and so on have been observed based on the some tests on different things. Homogeneous clay has been placed here in this particular figure, and clay sand plus geocell with reference to the original soil. If you are using the geocell, how much is the improvement we can see here. So for a very soft clay of 7 kilopascals, we can see the many folds. If you see about 40 kilopascals for undrained, unreinforced, with reinforced, it's obtained up to as a 350 kilopascals as a capacity enhancement. There's a level of enhancement in the case of very soft clay. So whereas though a very stiff clay of 60 kilopascals undrained shear strength, so the 200 kilopascals as unreinforced one, even the stiff clay, the capacity of the stiff clay could be improved to a significant level, almost doubled by incorporation of the geocell filled with the reinforced sand. So in the geocells, the confinement and interaction, locking, various mechanisms will occur. And the main mechanism which will dominantly we can see in the use of geocells is the confinement. Confinement is a special mechanism which will operate in the geocells to further enhancing its capacity. Okay, so this is how the confinement and along the walls that interface section also, and this geocell would be acting like a semi-rigid beam and dispersing the load to a wider area and enhancing the capacity. That's what the things will happen. The schematically one can represent by improving the area, confinement, interaction among the things. So how the shear could be developed can be represented in this one. So the effect of these geocells on the improvement has been studied as Professor Madhulata previously also mentioned. Some element tests and mode tests were done. They quantified the how much is the improvement in the strength with the in the terms of the delta sigma 3 lateral confinement effect and other ways, and evaluating its improvement effects in terms of lateral distant effects, how much is the vertical stress dissipation effect, membrane effect, etc. So which could be used to quantify the bearing capacity of the improved soil using the geocell approach, which can be obtained this one. So we also, this is to provide the comparison as a theoretical calculations of the bearing capacity obtained and the experimental observations for different configurations. So the reasonably, the theoretical evaluations and experimental findings are reasonably matching for a different settlement levels for different thickness of the level. So next configuration is geocell geogrid reinforced foundation system. So which has been presented here. As the interface is the geogrid reinforcement over that one. Geocell has been placed. And here you can see here the comparison here is shown here. The dashed line indicates only the geocell and the solid line indicates the geocell plus geogrid. So even though we have seen in the earlier series results, with the provision of geocell alone, it has significantly increased the capacity. The capacity has been further enhanced by inclusion of the base geogrid adhesives. For example, you can just see even the stiff soil now. This is only the geocell with the English geocell. This is the with the geogrid come geocell, the significant improvement what has been shown here. So this is for results of similar observations, varying different subgrade strength Cu of different values and different height of the geocells, and for different configurations has been presented here. Just to have a comparison of all the things in a one place. So this is for the very soft soil, 7 kilopascals soil, and you can see the unreinforced and original in situ condition. For very soft soil, how much is the bearing capacity has been obtained. And when you provided the sand, some top soil has been replaced with the sand, then we got some significant improvement. And then further adding the geocell and geogrid, how much is the improvement? Up to some deformation levels, geogrid and geocell are almost same. But if you are using them together, geogrid and geocell, you can see from the starting initial settlement level itself, there is a significant, very significant improvement in the capacity. This is for the case of the very soft clay, what we can see, what's the improvement thing. We can just see the performance, unreinforced performance is lowest, and the geocell geogrid performance is the highest level of improvement what could be obtained. These particular results are presented for the H, that is the thickness of the geocell, and the sand layer thickness is the 1.15D has been considered this one. So this is the next series for the 30 kilopascals case, that is where is the you can say is a medium stiff, what we can say. So even in this case also, you can see very significant improvement in the case of geocell and geogrid put together has been obtained this one. So similarly, the very dense soil or soft strips also we can improve the things. The contribution of different things in terms of either sand layer contribution, geogrid, geocell contribution, and geocell and geogrid contribution could be quantified with reference to the different reference parameters. So sometimes we can use the homogeneous clay bed as a reference, we can use the unreinforced layer foundation as a reference value. So we can get the improvement level of different contributions with reference to the earlier explained parameters, either bearing capacity ratio, improvement factors have been obtained. So the typical improvement factors, what we can see. So when your subgrade strength is very low, so you will be getting very high significant improvement factors, and in a moderately high subgrade strength, so you will be getting the relatively less, but still you are able to improve the capacity to much higher level, up to about 2 to 3 times it is improved. And for settlement level, these improvement factors would be enhancing with the settlement levels and etc. So these comparisons with reference to different subgrade strength, other things. So what they, I think so. So performance improvement also can be represented in terms of the reduction, percentage reduction in the pudding settlement. It is like improvement rate parameter, which can also be used for evaluating the capacity. So how much is the percentage reduction settlement also could be seen here. So here about 60% to 90%, a significant reduction could be obtained with the inclusion of different things. So what mechanisms operate, how they will operate quickly, let us have a look. And when you are having the layered configuration without reinforcement, so we can see the penetration at the interface, a significant penetration, and deformations are larger. When you are introduce the geogrid reinforcement, the penetration at the interface will reduce and a membrane effect would come. So this is a typical representation of the thing. So when you are having the geocell reinforcement, the penetrations would be much less, and a large semi-rigid beam type behavior could be seen, and the interface at the interface you can see the much less deformation. The super level of reinforcement configuration with the geocell and geogrid when you place, so you will be getting much higher performance, and you can see literally there is not much deformation at the interface, and loads are being distributed too wide. This is an unreinforced case. This is reinforced with the geogrid geocell thing. You can see the extent of the deformation at the interface and so on. In this case, there is an interlocking between the base geogrid and geocell can be seen, so which will be providing the much understanding. There is a possibility of top layers little buckling would be there, but doesn't matter. Your performance will be good. So with that, I conclude. So geosynthetic reinforcement, any form, is very effective in enhancing the foundation capacity. Of course, in the level of order, if you can see the things. Improvement or the performance depends on the footing settlement level. At what the serviceability condition, depending on the thing, whether 5% of the footing settlement, 10%, depending on that one, we can achieve the level of improvement levels. Of course, layer thickness and subgrade strength is important thing. What is the original interest? It's not necessary that only soft soils will be improved. Even the moderate stiff and very stiff soils also can be improved by inclusion of the reinforcement. So an improvement was decreased with increase in subgrade strength, as I mentioned. So they will provide the reinforced foundations, may provide alternate solutions, deep foundations under certain circumstances. One can look and adopt the thing. So with all these things, with these particular reinforced foundation would save the natural resources in some instances if it is avoiding the deep foundations, and also optimizing the cost and improves the structure performance. And moreover, it also demonstrates the resilience because it will have the higher capacity, higher things. Under difficult situations, it will take out and get the things. With this, thank you all for the patient hearing. Any more details about the publications and details of the studies can be found the publications which are listed in my website. So thank you all. Thank you, patient hearing.
Thank you, Dr. Krishna, for very insightful presentation. So moving on, I would like to quickly call upon our third speaker for today's session. This session will be given by Mr. Rudra Budbhatti, who will be presenting on advanced solution for hydraulic applications. Mr. Rudra Budbhatti is a technical head for McAfee Environmental Solutions Private Limited and has been over 18 years of experience in geotechnical engineering, including rockfall protection, landslide mitigation, soil reinforcement, slope stability, and erosion control. He has contributed to major projects, published papers, and serves on various codal committees. On this note, I would like to invite Mr. Buddhapati.
Thank you very much, Sumit. Hello and very good afternoon to everyone who has tuned in today. So my name is Rudra Buddhapati, and as Sumit explained, I head the technical operations for Macroferric India. I'm very grateful for this opportunity given to me to present to all of you very interesting presentation on advanced solution for hydraulic applications, where I will be focusing on the underwater solution aspects, along with a touch of the smart alert and monitoring system that we can integrate with such solutions. Sumit, I hope I'm clear and perfectly audible.
Yes, you are perfectly audible and screen is on full screen mode. It's perfectly fine. You can see.
Thank you. So in today's presentation, I'll be covering these topics. Basically, I'll start with a quick intro, followed by a glimpse of the recent developments that we have made for the hydraulic solutions. Then we will have a quick look at recent project experiences, and then the design tools, and then I will end it up with the smart alert and monitoring system that can be integrated with such solutions. So the effect of climate changes combined with the ever increasing requirements of urbanization often require in both rivers and the coastal environments to operate underwater. And operating in rivers or in general, like in hydraulic environments, projects often require to work partially or sometimes totally underwater. This means that we need to face more challenges as far as manpower is concerned. Another typical case is the production of bridges spanning across rivers, where piles require an erosion protection solution for its foundation. Even harbors and marine environmental areas are frequently required to increase and modernize their capacity, and hence require more erosion protection due to the increased effect of navigation. So the technological developments of the industry in the last decades focuses more on both environmental quality and on the sensitiveness of working environment through the risk assessment. So the research studies on erosion protection systems focus on the importance of resilience of the ecosystem to provide long-term economical, environmental, and social benefits. We have named this mission as Design the Change. With this in mind, while you know that the Gabion mattresses or Reno mattresses are quite common these days as hard armor lining, especially for bank protection works, we have researched and developed an improved type of mattress, what we call it as Reno Mattress Plus. Now let's have a look at what it is. So in this slide, you can see that Reno Mattress Plus, it has various components which are a little bit different from the standard mattress. Starting first with the double diaphragm. Typically, the mattresses are with single diaphragm. This is a double pleated diaphragm to make it more stiffer. Then we have X ties to connect the base to the lid, and basically also an improved version of the polymeric coating, what we call it as Polymac, to give it very good protection against the mechanical loads as well as chemical aggression. Because these are all hydraulic solutions and in constant touch with the water. Now, the high pressure resin polymer also makes the mattress, particularly suitable for river environments and even very harsh, polluted environments as well. The road to this development, meaning the Reno Mattress Plus, is not something which is, it's not something very old, in the sense that, of course, the first mattress version was developed way back in 1920. This was followed by the invention of Reno mattress in 1960. Then in the year of 1984, there was a test campaign conducted at Colorado State University to test the performances of the mattresses, to bring along a more scientific approach to the design. In 1980, the development of double diaphragm Reno mattress was done, and then recently in 2018, 2019, the research was conducted to develop the Reno Mattress Plus, to check its improved performances and how best it can help the engineers to design the solutions. So in the hydraulics of open channels, an important change over the years has been the creation of standards. So back in 1984, there were no specific rules to define the erosion protection systems and its performances. And the real design criterion for rock-based erosion systems in open channels was theory of tractile shear force, through which it basically uses the Shields parameter. So the mattress stability was based on the principle that the confined rock shall not move. Now, with the proliferation of the several types of erosion protection systems, required engineers to provide a guidance in their selection to guarantee a proper protection against erosion. So in the US, the most reference standard that is defining the performance limits of erosion protection systems in open channels is the ASTM D6460 that you can see on the presentation slide. So virtually all types of erosion protection systems, this is applicable, and this standard defines the stability of a lining when either no collapse or no erosion should occur underneath the protection layer. So the traditional riverbank solutions constructed with loose stones, or we call it as riprap, requires quite thick layers of materials to be effective. And with the Renomatrix Plus development, the thickness of protection can be drastically reduced, thus strongly reducing the material consumption. This very much optimizes the use of materials without compromising on the effectiveness of the solution, thanks to the better performance of Renomatrix Plus. And this, of course, brings along huge amount of cost savings. Now, let's see which are the results in terms of numbers. So this slide basically gives a representation of thickness versus the maximum shear stress, which has been checked for its performance. So the first one, which you see in light blue color, is the test campaign in 1984 with the mattress with single diaphragms. You can see the the maximum shear stress values here for that, which is in around 200 pascals. Whereas in 2019, the double diaphragm improved its performance significantly from close to 200 to almost 300. And then the recent developments of Renomatrix Plus with X-Ties drastically improved the performance further, right up to 450 pascals with just a 0.17 meter thickness. So as the thickness increases, of course, the maximum shear stress which it can take also increases, and there's a significant improvement in the performances of mattress as the development has been done for Renomatrix Plus. In essence, the shear stress that we are talking about is the force of moving water against the bed of channel that causes erosion. So once the importance of the evaluation of shear stress is defined for Renomatrix Plus, we can refer to the values obtained in this research, and then accordingly the selection of the thickness and the type of mattress can be done. Now further to this development, we also developed a pre-filled underwater solution, what we call it as Renomac Plus. So basically an effective way for installation of erosion protection systems underwater is to assemble the components with the right equipment in a controlled and dry environment at a site close to the project site, maybe on the banks of a river. And then the let's say the pre-fill units are lifted to the site where they can be installed and launched underwater by means of suitable equipment in the form of cranes and lifting frames that you can see in the picture, along with the assistance of divers, which are typically required. So to this scope, Renomac Plus especially designed mattress unit to help with the underwater applications of the solution, especially to provide erosion protection of the bridge piles, quay walls, marinas, eroded banks, etc. When the project requires construction of an underwater retaining structure, a pre-filled special grievance may be used, what we call it as QB-MAC. Basically, they are made with wire which is bigger diameter than conventional grievance to resist the high stresses and to keep the uniformity of the shape when the lifting is done. Because otherwise, if the wire is not stiff enough or the mesh is not stiff enough, there will be a lot of deformations happening when the lifting of a pre-fill unit is done. Now, what are the benefits of pre-fill solution? Pre-fill solution, basically with the help of Renomac Plus or QMAC, brings along numerous advantages. Launching, of course, is much easier, and insulation is much more accurate than many other conventional alternatives. So overall, the construction leads to competitive benefits like, the design optimization aspect. It's very easy and safe to install as compared to other conventional solutions. And yes, also the lifespan is large. So this all leads to, the optimized total cost of ownership. Once the pre-fill units are filled, basically they can be stocked at a convenient site and then transported. So here you can see examples of Renomac Plus on the left, which is pre-filled and ready for transport. And on the right, you can see the QBMAC, which is again a pre-fill unit, and it is in stock and it can be quickly transported to site. As previously said, the Renomac Plus is a special unit designed for insulation underwater, and there are certain peculiar characteristics. Some part, of course, is something similar to the Renomattress Plus that we saw earlier, meaning that yes, it has the double diaphragms, which confine the stones in a much better way, since it's more stiffer than single diaphragm. Then we have the X-Ties, which will greatly improve the adherence between the bottom and top panel, further increasing the stone confinement during handling. Plus, what you see at the base is geotextile filter, which is pre-attached along with the extended panel at the base to keep the continuity of the protection between adjacent units. Because do remember that when we are talking about underwater application, many times it's not feasible to do the lacing of the units together. And hence this extended base is required to have the necessary overlap and prevent erosion between the units that are placed adjacent to each other. The rebars then are, of course, added to help with the lifting. They are assembled as part of the system only, and then they help in providing the uniform distribution of stresses during the lifting operation. So all this is let's say, prefabricated in the factory itself, and then all that is required to be done on site is open it up and then do the filling of stones and finally attach the lid. That's all. The lifting frames are sized to basically best suit the dimensions of the unit and to the lifting equipment, that is the crane. And lastly, of course, the air resistant coating is important to boost the performances against the abrasion effects. Now, I will show you another interesting development in terms of the performances of Renomac Plus. So, I'll give you now an overview of the research that was done in 2023 with Deltares, where the pre-fill mattress design, basically the understanding of its performance was done against the jet propeller actions of the berthing vessels. So in this video, you can see that the deformation test conducted on scale model in the lab. On the left, what you see is sand bed without any protection. And then you can see on the right, the bed which is protected with a Renomac Plus unit. And on the left, you can see substantial erosion is happening. So on scale, basically almost 3 meters of erosion happened, whereas in the case of a protected layer, even with a higher velocity than this one, there was no erosion. You can see some bubbles which are there of the moving propeller, but otherwise there is no erosion happening on the bed. You can see here some bubbles, so you can see that's the effect of the propeller, but zero erosion. Whereas on the left, you can see substantial erosion happening. So the outcome confirms the evaluation method with updated resistance parameters for the design of Renomac Plus for such applications. And this allowed for the validation of the resistance parameters. So with these tests, we have seen in real way what are the actual behavior of this kind of a solution. And based on the guidelines provided by PIANC, the recommended design formula is derived by Pelagic studies. In this formula, the minimum required thickness of the protective layer, which is defined by D, is basically a function of various parameters and coefficients. Among these, the velocity at the bottom is the main forcing factor in relation to the shields parameter, which represents the strength of a chosen material. So the minimum thickness of the protection is thus inversely proportional to the critical shields parameter. The new parameter defined through research for Renomac Plus has a much greater value, which you can see now on the screen. So the critical shields parameter for riprap is 0.035, for concrete mattress it is 0.07, and Renomac Plus it is 0.19. So with this you can see that there is a substantial reduction in thickness that can be offered by utilizing Renomac Plus as a solution. So under the same conditions, the minimum thickness of protection with Renomac Plus is up to 7.5 times less as compared to riprap solutions, and twice as much less when compared to the concrete mattresses. This is of course based on the studies that have been done. This therefore introduces a considerable cost and environmental impact savings by reducing the amount of material required to create the protection. Now let us have a quick look at Cubimac as a unit. So in terms of the structural strengths of Cubimac, basically, as I was mentioning earlier, it is made with a bigger wire diameter, 3.4 or 3.9 mm, making the overall robustness of the cage particularly suitable for handling phases for lifting and launching. Typical meshes otherwise are of 2.7 mm wire diameter, just for reference. Then there is also the lifting slings, the bar at the base, and there's also the additional base panel, bottom of the basket, designed to firmly anchor the slings at the bottom of the unit. This ensures safe and sound use, so that there is no issue at the time of lifting and it's perfectly safe. And of course, the coating is of Polymac, what is something which is recently developed again to boost the performances against the abrasion effects. Just to give you a quick comparison between Polymac coating and PVC. So Polymac, of course, has over 120 years of design life, and it is having 12 times better resistance to abrasion, including installation damage, 23% harder than traditional polymer. It has even better performances in cold weather, and it has more resistance to UV rays, making it, let's say, better coating in all the different kinds of environments possible. Now, let us have a look at some of the case studies, which I believe you will find it interesting. So, I know first I will start with a case study for a bridge pier protection in Bordeaux, France, on Garonne River. So here in this case, the shear stress is acting on the foundation of the bridge piles required an erosion protection measure, and Renomac was chosen among the alternatives that it could provide the continuous protection on the bottom due to the overlap of the units, because there is an extended base with the additional mesh and geotextile present. So Renomac significantly reduced installation time, and this was a plus due to the limited time to work because of the tidal flows coming in from the ocean a few kilometers away. Units were basically filled on the riverbank, and the installation underwater was performed with the assistance of divers. Compared to the traditional loose stones of larger size, this solution basically allowed, let's say, a solution wherein the requirement of maintenance or replacement over time was not there. Because with traditional loose stones, more often than not, at a frequent intervals, we need to carry out maintenance. Some stones, if they have rolled away, we need to replenish them. So all such things can be avoided with the installation of Renomac unit, because it's a confined solution. They also, of course, require lesser amount of filling material, approximately 70% less, based on the performances that we have seen, as opposed to the conventional loose one. In short, there are three key factors of success. One, of course, is that Renomac is a ready-to-use solution, not requiring any special assembly on site, because it's a pre-manufactured unit. It helped in reducing the preliminary earthworks and avoid risk of damage to the foundation, because it's a modular structure. And the volume of stone is drastically reduced as compared to the equivalent performing protections by up to 70%. This is another case study of a project which is located in Arles in France. And basically, the location is such that it is crossed by Rhone River in a section close to the sea. The port along the river has a quay wall, which requires some protection measures to prevent scour generated by the ship propellers. So why is actually riprap best preferable as a solution for applications on long slope banks? The reason being that, to prevent the rocks to become unstable, it has to be extended right up to the bottom of the slope. So the complete slope up to the bottom will need protection, even though the actual area subjected to erosive forces may be only this much, what you see here, which is subjected to erosion. But if we place the stones just here, typically they roll down and then this will be exposed. So hence we need to protect the full slope with riprap, if riprap is used as a solution. So why Renomac Plus was a preferable choice? Because we can treat specific area which is subject to erosion, and you don't have to extend the protection up to the toe, and leads to savings plus the reduced thickness. And how this is done? This is done with the help of what you see here is the placement of unit starts from this point onwards, and then it is anchored to the top with the help of the pre-filled Gibbon unit, which is called as QB. So this act as an anchorage, and then this anchorage prevents the sliding of the mattress further down. Of course, we can check the sliding potential of the mattress by doing some stability checks. So with this, the overall solution was optimized as far as the length is concerned, and also with respect to the thickness. The third case study is a project in a challenging climate in Abidjan in the Ivory Coast in Africa. Part of the port rehabilitation was done because there was a need to increase the navigation capacity, and this required to build a 450-meter long, 16-meter wide jetty where the boats could dock in a cave which was 8 to 10 meters deep. So the design required a protection of the seabed along with the quay wall against cover generated by the boat propellers. So Renomac was chosen among the solutions, and the units were pre-filled on the shore, and then it was launched with a suitable frame. Now, there were three key factors leading to success for this project. Number one, the thin layer of Renomac as opposed to the equivalent rock layer allowed to save material and time in setting the foundation. Plus, it also allows the accommodation of larger vessels because it can save space. Because the thickness required for Renomac Plus versus the conventional is drastically reduced, so there is space available to accommodate larger vessels also. By laying the units adjacent to each other on the overlap, so that made it very convenient to do the installation, simpler to do the installation as compared to conventional. And the design, of course, was done through the Planck report 180. This report basically gives a detailed background information about the vessel propulsion, allowing an effective design of the quay wall protections against erosion. Now let's have a look at case histories related to QBMAC units in underwater applications. So this one is in Stuttgart, Germany. The project is a part of a 1,500-kilometer long rail link connecting several cities in Europe, and consists of rehabilitation of the rail network. Part of this project was the construction of a new railway bridge over the Neckar River, and the construction of the bridge required that the bridge foundations were to be built in the middle of the river, and the design included the construction of an artificial piece of land protruding into the river, and that land was to act as a temporary platform for the construction operations. So QBMAC units were used for a major part of the project, as the requirement was to operate mainly underwater. Divers were required, and they assisted to ensure that the correct installation is carried out. The key factors which made this a very good choice was that yes, it is a permeable structure allowing the water filtration with an excellent resistance to high loads, and being ready to use, QBMAC units are ideal to follow the progress of the construction, so they can be easily and quickly launched as per the requirement. As the bridge was completed, the artificial land was removed, and the QBMAC could be reutilized in other project phases as well. So this was an added benefit. And now this is another case history of a project which is located between Brittany and Normandy, again in France. In this area, the Sélone River flows into the bay, carrying considerable amount of sediments. And for this reason, a solution was required to prevent the polluted sediments from flooding into the bay area, and and to avoid the water contamination. Closer to us, so this is one case history in India where the project is still ongoing. There is a project ongoing here at Guwahati on the Brahmaputra River, where there is a severe scouring issue at one of the piers in the bridge, which is under construction at this point of time. And this required erosion protection works to be installed at a depth of 35 to 40 meters underwater. So in this case, a pre-filled mattress, something similar to what we call it as Rhinomat, was used. And you can see here, this is how it is shipped from the factory. You just have to open it up, fill the stones, and then it can be lifted and placed to the project site at the pier location with the help of cranes and lifting frame. This is still under way in terms of construction, and so far it's working fine. Now, with all these, let's say, updations, we have also worked upon our software suite, which you can access online on edesign.macafin.com. There are several softwares available for your use. You just have to create a login with your email ID, and you can start using these tools for free. Among these tools today, I will be mainly focusing on the hydraulic design tools, which is the Mackey design and Macra design. Let's have a look. So Macra design tool is basically a tool developed to help design the channel and bank protection works. We can basically do the cross-section analysis for the longitudinal works. Basically, the free surface channels with steady, uniform, turbulent flow. This is the criterion with which it can do the analysis. Now, the cross section can be, modeled as per the need, as per the let's say the project requirements, and it can be lined with specific material to emulate the erosion forces. And you can do a lot of permutation combinations because this accurately models the tractive shear force across each segment of the channel rather than the conventional tools. For example, Hectress is giving the shear stresses for the full section, not individual sectors in a particular channel. So that's the main difference and an advantage, wherein you can do a lot of optimization by doing the design in this case. Of course, it has been also compared with Hectress, and then there is hardly any variation of the overall output. So it is well aligned as far as the accuracy is concerned with the conventional tools. Apart from the longitudinal structures, you can also design grade control structures of different types, be it vertical drops, stepped or sloping weirs, along with the design of the dissipation or the stilling basins. So this software, is quite easy to use. Of course, you can always reach out to us in case you need any specific support or training on this. More importantly, there is also the help menu, which is there, which gives the inputs related to the full detailed manual of the background of the calculations, plus the user manual in terms of how you can use the software. Both the manuals are part of the help section online on the software, so you can always refer to that as well. The data entry in this tool is very simple and very intuitive. The user basically needs to enter the cross-section dimensions and then some basic information like hydraulic parameters such as the discharge and the average gradient for the cross-section. Ultimately, and of course most importantly, type of material present on the riverbank. So the user has a possibility to choose from a wide database of erosion protection systems, including natural soils or green systems, either in the initial stage of recovery, let's say for example the bioengineering, or you can also model the section with the protection systems like Nanomatrix Plus and such. Similarly, Mackie is a design tool which you can access, which is related to the port engineering. This software focuses on the design of protection systems against cover caused by the propeller action of the ships at the berthing structures. So this software can basically analyze different types of berthing structures like vertical or sloping, and we can simulate also the different types of vessels. Again, the data entry is very intuitive. We just need to enter the geometry of the key, can input the vessel type, and then the materials in terms of erosion protection materials which are available in database, so that you can model at the base of the key, and then you can do the checks. Now I will move on to the last part of the presentation, which is smart engineering based on IoT technology. What we call it as HelloMac Hydro. Now, basically, I'll give you an overview of 4 main applications of HelloMac Hydro. The first application that we see here is the smart bank protection. So in this application, the HelloMac Hydro makes the gibbons and mattresses smart by integrating a simple non-invasive sensor that triggers an alert when the water levels exceed a predefined safety threshold. There are many suppliers of monitoring devices in the market. The key advantage of this particular system is that it's based on IoT connection, and then it transmits the data to the cloud, which will give you a very, very quick alert in matter of seconds, and also provides an early warning to alarm in case of a flood event. The kit includes the piezometric sensor, what you see here, and also the transmission device. And this transmission again is, as I was mentioning, it can be through the transmission can be through the IoT interface, or also it can be linked to other cloud ways of connecting, in the sense that it can be through 4G or satellite. There are all the options possible. Standalone system, basically, this particular standalone system is capable to transmit, as I was mentioning, via GPRS directly to the cloud, or can be used in a network of water level measurement using a peer or a gateway that can have a connectivity of satellite, and also the GPRS. Now, a few elements of each kit. It's basically composed of 2 elements. One is the sensor, and then the radio interface. This is the radio interface, what we call it as SFL. It's very easy to use and install. It can be installed in just a matter of 20 minutes. And the water level at the time of installation is required, so that it can be set in the software on the cloud. There is no other, specialized technicians required and such things, making it very, very convenient and easy to install. The second application is related to smart bridge monitoring. Some aspects were shown in one of the presentations yesterday. I'll just quickly run through it. So the HelloMac Hydro for bridge application combines the monitoring with an early warning system designed to detect potential scour issues before they escalate and create a lot of structural issues into the bridge. This system is capable to detect erosion at the bridge piers and the water level changes. So the solution features a lightweight, basically very compact, easy to install device connected to the river bed near the bridge piers. And this device essentially detects erosion, and if it exceeds a defined threshold, it will give an alert. Additionally, the system also includes ultrasonic or a radar-based water level sensor that is mounted near the bridge deck, ensuring the early detection of rising water level. So in case of a flood, it can give warnings and alerts to the users of the bridge to be careful, or if needed, authorities can also shut down the operation of the bridges. So by integrating these kind of components, HelloMac Hydro offers basically all-in-one innovative and low maintenance solution that provides reliable safety for the bridges. So in terms of smart bridge monitoring, this is what it is composed of. Of course, it's a complete system for bridge hydrometric level monitoring and bed erosion. Both are included in the same network, and all the devices again are based on IoT technology, which is connected to the Hubir, which acts as a sort of a collecting hub and transmits the data to the cloud. And that transmission can be via GPRS or satellite. This Hubir can be installed into a radius of 5 kilometers from the bridge. So it can be also installed at a safe location far away as well. In terms of the elements of each kit, so there are 3 elements in the kit. One is a water level sensor, the radio interface, and the scour detection sensor, and plus the Hubir. The water level sensor can be ultrasonic, which has, let's say, a coverage of 0 to 6 meter, or it can be radar, which can have a coverage up to 10 meters. And there is a possibility to use extra scour sensors also for multiple bridge pairs. It's again very easy to install and use. It's just a plug and play system. And once installed, it is immediately in operation. In terms of flexibility, yes, you can also integrate the system with local alarms, and you can integrate it, for example, with sort of traffic lights or some sirens, however you want to have an alert getting created locally, apart from you getting the alert via the SMS or through the app or an email, however you want to configure it. Now, the third application is the smart quality monitoring. Let's have a look. So this solution offers versatile quality water quality measurement kit with a multi-parametric probe capable of measuring up to 7 parameters. And these parameters are like the pH, the conductivity, redox, dissolved oxygen, temperature, piezometric level, and also there's an option of turbidity. So this system is again equipped with an inbuilt IoT transmission system to send the data to the cloud platform through a data logger. This system is powered by a solar panel, and there's also backup of extra batteries. So the integration of technology and environmental management is essential to safeguard the ecosystems and ensure regulatory compliance, combining the structural protection with also such advanced quality monitoring potential as well. So in terms of the kit, it is composed of 2 elements mainly. One is the sensor and then the data logger. It's very easy to use and install, just like what you've seen in the other systems. Installation time here in this case is very quick. Also, it can install in 3 hours, and the water level, of course, is required to be provided as an input so that it can be set on the software. And finally, the last application which I'll show is the smart key monitoring. Let's have a look at that. So Halomac Hydro provides an advanced solution to monitor the safety of the ports with an early warning system for scouring near the key walls. This system has been designed and developed with a simplicity and modularity to be installed in a number of required locations, and then it can be used to monitor multiple points of interest along the key wall. The system features basically a lightweight, compact, and easy to install device, something which is basically similar to what is there, what we saw in the smart bridge kit. The same device can be used to monitor the scouring action at the key walls as well. The activation of alert system is, of course, guaranteed by the electronic sensors, and then it will immediately send an alarm once a certain threshold is getting crossed for the erosion. So by integrating this system, Halomac Hydro provides a lightweight, compact, easy to install device connected to the seabed. By integrating this early warning system, it contributes to the long-term stability and safety of the port infrastructure. In terms of elements, each kit has one element in the sense that there is the scour sensor plus the Hubir, which is the gateway that transmits the data. There's also, of course, the possibility to add extra scour sensors to monitor multiple points that I have shown. And it's again plug and play based on IoT, and you can also have local alarms set across through the Hubir, apart from the online alerts that you can get. Now, all these systems that you have seen are based on IoT-based principles, just to remind you, and can work on 5 different types of network, be it GPRS, 4G, satellite, LoRaWAN, Wi-Fi, and high-speed connectivity is guaranteed in all potential, let's say, project environments and areas. The transmission of signal to the cloud is done in a matter of few seconds, and you will get an alert, in immediate basis. The alert can be had through an app which is available online on the app stores of both Apple and Google, via an SMS which you can configure, and also the email. Apart from that, we can also see the, let's say, different sensors on the dashboard as well, which is online. So basically, you get real-time insights at your fingertips, and you'll always know where the sensors are located, which sensor is activated, what are the measurements, by just having a look at the app. With this, I end my presentation. Thank you very much for tuning in. And during the question and answer session, I'll be more than happy to answer to all your queries. Thank you very much.
Thank you, Mr. Badbati, for a very nice presentation. We could see various images, illustrative representation of the solutions. So I think with this, we can conclude our first three presentations that we have. And now we can quickly move to the Q&A session. So just give me a while. I'll just start with the Q&A section. So we have our first question from Mr. Hosamani. Question is, how should be minimum ratio in unreinforced soil to reinforced soil to achieve the enhanced soil bearing capacity of RE wall foundation? And this question is to Dr. Krishna. We have him in the panelist.
Yeah, he's there.
Dr. Krishna, would you like to take this? Okay, I think he might be facing some issue. So in the meanwhile, we can continue with the rest questions. So I would request Mr. Tanmay, if you can check with him, or maybe we can assist him with some support if in case he's facing some issue. Okay?
Yeah, I'm doing that.
Yeah, thank you so much, sir. So now moving on to the next questions that we have. So I think this question is to Mr. Bodbati, and the question is how to ensure that the rock fill with the mattress will remain stable under design flow velocity and turbulence.
Yeah, so basically the stones that are filled within the mattress remain stable. Of course, there's to the stability of it, and the limits are defined by the testing that we have done. The main aspect of stability of the stones, or let's say prevent movement of stone, is the confinement which the mesh offers. Now, with the development of Renomatrix Plus that we have seen, we have also stiffened up the diaphragms to have a more stiff basket in which the stone movements is minimized further. Apart from that, we are also introducing the X tiles that you have seen in the presentation slide, which basically connects the bottom panel to the lid, and that introduction again improves the confinement of the stones and preventing its further movement. So there are predefined limits, of course. It's not like in all possible or very high velocities it will not move. But the main idea of providing a erosion protection measure is to ensure that no erosion happens below the placement of the mattresses.
Okay, So next question, thank you for taking the question. So next question that we have from Mr. Mandal, and the question is, what is about the long-term durability aspect of Renault mattress in case of alternative drying and wetting condition, specifically in case of using the bank protection and in case of using channels bank bed containing chemically contaminated water flow. This question is to you.
All right. So we have done testing for the polymac coating to cover variety of chemicals and plus the alternate wetting and drying through a neutral salt spray test, wherein it has been tested now for almost 20,000 plus hours, and there has been no rusting found, and still the test is continuing. So we have not yet reached the threshold of formation of rust yet with the polymac coating based on the testing. Yes, the exposure to different chemicals has been also tested, and it is remaining neutral. We can share with the person who has asked the question more data in terms of which are the chemicals which has been tested, and there has been no effect on the coating.
Okay, thank you. So next question that we have is, what is the criteria for selecting geotextile under submerged water conditions? I think
Can you please repeat?
I think Dr. Murli, you're back. Or maybe the issue is resolved.
Hello?
Yeah, am I audible,
Yeah.
sir?
Yeah, audible.
Okay. So we can take questions for you.
Yeah.
Okay, so I think we are in mid of a question which Mr. Budbati is just answering, and there are a couple of questions, and then we can come to your Q&A. Okay, sir. So yeah, Rudra sir, if you can
Yes,
continue,
yes.
please.
Yeah, I was since there was some disturbance. Can you please repeat the question?
Yeah, question was what are the criteria for selecting the geotextile under submerged condition?
Yeah, so when it comes to geotextile selection for submerged condition, especially for erosion protection application, the thickness or the opening size of the geotextile is important because it needs to be robust enough to, number one, not get affected by the insulation damages which are likely to occur, and also it needs to have resistance against the other things, like for example the chemical action depending on the type of water it is getting exposed to. And apart from that, that geotextile needs to act as a sort of a protection against the scour, or it needs to act as a filter. So so as I was mentioning, the opening size of the mattress of the geotextile also matters a lot. Typically in the usage of a geotextile in a submerged condition, it is not used by itself. Typically, it is used with the solutions that we have seen. If it is just laid on the bed, it will tend to float by itself. I mean, it won't function properly. It needs to be anchored so that it can function.
Thank you, sir. So next question that we have is again to Mr. Rudra. Question is, how to ensure that aquatic life is not affected using these solutions?
Yeah, so what we are seeing today are solutions which are quite environmentally friendly, and in the installations that we have done many years ago for such applications, be it for bank protection works or be it for marine applications, certain marine applications, we have seen that there's a very good growth of vegetation happening. Even the sea life or the marine aquatic life is not at all affected. Seahorses are also made homes in in the mattresses which have been installed. So in that sense, it is quite environmentally friendly. Even the materials that we are using in the manufacturing are again environmentally friendly. So in that sense, it is performing very well without having any effect on the environment. Plus, it's not just having any adverse effect; it is helping the environment to improve because it integrates the vegetation very nicely.
Thank you, sir. So I think we can take next set of questions from uh, Dr. Krishna. Just a second. So question is, can the width of the reinforcement in foundation soil can be reduced by wrapping the reinforcement on both sides suitably within the available width of land available of the structural foundation? Does there will be any reduction in effect of reinforcement for increase in BCR and reduction in total settlement?
Can you say again?
Yeah, why not, sir? So question is, can the width of the basically these are two questions. I'll take one by one. Okay, sir. Can the width of the reinforcement in foundation soil can be reduced by wrapping the reinforcement on both sides suitably within the available width of land under structural foundation? This is the first part.
No, there should be some additional length is required. Structural foundation only just below the foundation. If we are using the geocell, there is no issue of wrapping. To some extent, it will be improving the bearing capacity. If you are having sufficient length beyond the structural size of the foundation, the reasonable improvement can be obtained. I think wrapping the thing is now, I'm thinking that thinking of a planar reinforcement, you are trying to wrap the thing because of availability of the space at a particular area. Yes, if the restriction is there, then we can attempt it. Obviously, it will improve. It's like, again, you are confining the area and you're trying to achieve the improvement. Yeah, under restricted conditions, yes, we can go ahead, but the level of improvement would be something different.
Okay. Thank you, sir. To now taking the second part of the same question. Question is, does there any reduction in the effect of reinforcement for the increase in BCR and reduction in total settlement?
Increasing in BCR, reduction in
total settlement.
Can I read the question here?
Yeah, you can, sir. You can. You can go to the Q&A section at the bottom, and there you can. So basically, in the meanwhile you are finding it. The question is from Mr. Avik Mandal. Question want to say that what will be the impact on the effect of the reinforcement if we increase the BCR and reduction of the total settlement? Please, sir.
Increase the BCR and reduction in the total settlement. They are the output parameters. Obviously, along with that one, for a given configuration, depending on your allowable settlement, we have to choose the level of reinforcement. Now, from the results what we shown, the effect of reinforcement and settlement level will show that depends on the improvement level. There. Okay. So, what is the serviceability settlement allowed, and how much is the original settlement without the reinforcement, without the improvement level? So, those two levels will decide, of course, your settlement ratio. And as per the condition, site condition, okay. So, whatever the in situ capacity levels and what is the type of the reinforcement we are adopting, accordingly, we can choose the reinforcement. Okay. The thing is, of course, it's not the effect of BCR and settlement reduction is deciding the reinforcement. Of course, we'll do trial and error way. We'll come back again.
Okay. Thank you so much, sir. So we'll be now taking the final question of the today's session, first three session, and the question is, sir, can we replace matte foundation in black cotton soil using geogrids?
MAT foundation using yeah, in principle,
GeoCell
yes,
geometry.
MAT foundation can be avoided by using the GeoCell is a semi-rigid platform which will be created, but the condition is no black cotton soil. Okay, so of course we are significantly replacing the top part of the soil when we are going for the GeoCell reinforced foundations. Top part of the soil will be replacing the thing. The expansion effect will be significantly reduced, and it will be good some treatment to the black cotton soil to avoid the expansion of the thing. If we do that one in combination of using this one, it will be much more beneficial. Yeah.
Okay. Thank you so much, sir. So I think with this we can conclude first half of the today's session. And I must say that I must say thank you to all the speaker, Dr. Madhvi, Dr. Murli, and Mr. Ruth Bandwati. So and I must say we are concluding on very much on time. And now with this we can break for lunch or break. We'll be having a 1 hour break, and we'll be starting our next presentation, which will be given by Dr. Venkat Udakala, sir. And before that, I would request for that, please join at least 10 minutes before, because when we join prior, we can start on time. And also one more announcement for everyone, that after Dr. Uday Kala's presentation, we will be having a quick smart quiz, which will be for 20 minutes. So please be available during that quiz. And towards the end of the session, today's session, while concluding our 2-day Reinforce 2025, we'll be announcing the winners as well. Thank you so much. Let's connect at 1:50.
Yeah, thank you. Bye bye.
Thank you. Thank you.
Thank you. Thank you all.